in this episode of the Critical Oxygen Podcast. Probably 30 watts, do 3 minutes, bump up 30 watts, do 3 minutes, and keep doing that until failure. And then you're going to look for, exactly like what you were saying, those changes in steady state from maximal oxygen levels to, then it's going to come down, and then it's going to potentially reach like lower oxygen levels where you can actually reach a plateau in a steady state, and then it's going to hit that tipping point. And now you have your zone 2 training. So, like the power or the percentage that you're going to work at for your zone 2, you have your, an idea of where your threshold is, and then you also have the VO2 max, SMO2, so now you can hit all 3 of those types of workouts. And all you need is just a little NIRS device on your leg. Welcome to the Critical Oxygen Podcast, where we help you optimize your physiology and maximize your endurance potential. I'm your host, Phil Batterson. I have a PhD in molecular exercise physiology, and I'm the founder of Critical Oxygen, where my mission is to build better endurance athletes through remote education and in-person physiological testing. Today, I'm joined by Dr. Andri Feldman, where we discuss the importance of oxygen and how to measure oxygen dynamics in the muscle using near-infrared spectroscopy devices like Moxy Monitor. Dr. Feldman is currently a sports scientist for Swiss Athletics and a staff physiologist for Moxy Monitor. He completed his PhD at the University of Bern, where he studied the effects of different exercise modalities on the muscle oxygen response. Andri and I have worked together and even published papers together, so I'm super excited for all of you to hear his expertise. Overall, Andri is a wealth of knowledge and a true expert when it comes to NIRS. So without further ado, enjoy our conversation all about the importance of oxygen and how NIRS can measure oxygen dynamics during exercise. Enjoy. Dr. Andri Feldman, welcome to the show.
Hey, Phil, how are you?
Good, man. Thanks for coming on. This has been kind of a long time coming. For those of you who don't know, Andri and I have actually collaborated on a paper before where we looked at, the prevalence or the relationship between Moxy or SMO2 slope and lactate values. So anytime you've heard me talk about lactate on the podcast, and I always have a tendency to be like, well, I think NIRS is actually, just as valuable as lactate, if not more. One of the reasons for that is some papers and a lot of discussions that Andri and I have had together. So, Andri, if you wouldn't mind, just introducing yourself very, kind of briefly to the audience. Why are you so into physiology? What do you do currently? And how do you use kind of the things that you learned in physiology for either your own training or your athletes' training?
Thanks for having me on, Phil. So you've asked me a long time, and I said I would come on, and we've pushed it a bunch of times, so it's kind of my fault, because I don't have any time. But I'm happy I'm on now. I did a PhD at the University of Bern. Maybe I'll start my story a little bit before that. I grew up in northern Canada, and my dad was a physiologist, a physiotherapist, Jörg Feldman, and he did a lot of pioneering work with blood lactate sampling. I started blood lactate sampling when I was about 13 or so, because my dad needed help sampling athletes. So we'd go to these training camps. They'd be like, we'd do dozens of lactate tests every day. And so as soon as my dad felt I was able to, I would start blood sampling. So I started that physiology path pretty early. I kind of pushed into that, which is okay. And then I did my undergrad at the University of British Columbia, where I also then picked up on NIRS. My dad also pioneered some NIRS work, and I did some stuff at the university as well. That's where I ended up getting to know Roger and Moxy in prototyping phase, and that's also where I got involved with the Moxy Monitor, as a disclosure, and where we also then got to know each other, right? Doing the work with Moxy. And then I did my master's in Switzerland at the University of Bern. And then I had my own training company where I used NIRS in training with athletes. And then I went to do my PhD based on, 5 years of in-field experience with NIRS. I decided I wanted to go do some more research. And now I work for Swiss Athletics, which is the Swiss Track and Field Association, where I'm a sports scientist. I'm actually, next week is European Championships, so I get to go to Rome for a week. Should be fun.
Awesome.
But I don't actually do a lot of work with NIRS with the Swiss track team. So I do different
Yeah.
analysis, not actually NIRS stuff. I work mostly with sprinters and kind of bigger picture projects, lots of like data science stuff. Actually, a lot more of that. So that's a quick overview of where my life is at.
Yeah, that's really interesting. And so you got into Moxy when it was in the prototyping phase. So you've been around since the inception of it. Um, and we'll talk more about Moxy in a little bit. But that's just really interesting because I was trying to figure out, when I was like, thinking, okay, Andri's history and stuff. Like I knew you'd been around doing lactate samples and other things like that, but I didn't know you were like in on the ground floor with Moxy and the development of that technology. So that's really cool. And then you said you don't really use NIRS, but during your training or your like most of your research though was in near infrared spectroscopy, right?
That's what I mean by don't do NIRS. It means like for the Swiss track team, I'm not the coach. Okay, so I'm not the one
Right.
working with the athletes directly, and I don't impose my ideas on the coaches. Okay, so if I was the middle distance coach, I would use Moxy or I would use NIRS. But
Yeah.
I'm not there to impose that. I first of all, I don't work with the middle distance runners really. I work with sprinters mostly, which you could talk about usefulness or not, different conversation.
Hmm.
But I'm there to work on goals that we have as an association and not work on my goals for NIRS. I still do NIRS work.
Right.
I still
Right.
do stuff with Moxy. I've got a bunch of projects running at the university as well, which are all NIRS based projects. So NIRS is still a big part of what I do. It's just not in focus for, let's say, my day job at the Track and Field Association.
Yeah.
That's
Yeah.
that's what I mean.
Yeah, that makes a lot more sense. And I think, we've been kind of just like throwing out NIRS and other things like that. But what I want to establish first here, is let's take a step back and let's talk about the physiology of oxygen and why oxygen is so important. And this will come into play when we start to talk about oxygen consumption and NIRS and how we measure it. So I want to set a good foundation for people to understand, the importance of oxygen for, exercise and particularly endurance performance. And, we can use endurance performance kind of loosely. But yeah, so in your own, sort of ideology or your own words, why should we appreciate oxygen and oxygen consumption, and really like what is like the underlying physiology behind that?
It's loaded as a loaded topic.
Yeah,
Um,
yeah, yeah.
so it's obviously very complex, but I think because we were talking NIRS and NIRS measures muscle oxygenation, so this idea of, well, why is that relevant? Why is oxygen relevant? I think is important for people to understand. And I think we all know oxygen is important because we breathe, we need oxygen. So obviously, yeah. I don't think we need to discuss that we need or don't need oxygen, which we'll get to this weird concept of anaerobic and aerobic, but we'll get to that a little bit later. But I think we can start with a little bit is like, okay, we have oxygen, we know oxygen is important, and then it's for basically, why is oxygen important? It's important because it makes energy for us. Okay, we need ATP, we need energy.
Hmm.
And it's like, okay, what does that mean? What does making energy out of
Right.
oxygen even mean? Right. So now I don't want to get lost in infinite regress because, again, at some point I don't understand what's going on either. I struggle enough with understanding what's going on with what I'm going to try to explain now. So, but let's because again, I'm not a biophysicist here. But basically, we talk about what's important for oxygen. You say, well, it's the final electron acceptor. That's what you then read.
Hmm.
That's why it's important. It's like, okay, what does that mean? Well, if we think about energy, we think about, like, for example, electricity. And electricity can be looked at as like a flow of electrons, for example. If you have a flow of electrons, you generate voltage. And you can do experiments with this. So you have solutions. You can have oxygen, which is this high electronegativity. And you have a solution that's like hydrogen, which is a lower electronegativity. Has to do with protons and electrons. So
And
oxygen
how
would
well
have
they pass them
eight.
back and forth, right?
Exactly. Yeah. So
Yep.
oxygen has 8 protons and has 6 electrons in its close ring, right? But it needs 8 for stabilization, so they come together. That's why you always have O2 and not just an O. right? And so this is why it's got this high electron activity. It's pulling electrons towards it. Okay, so if you make this solution with hydrogen and oxygen, you then get a flow of electrons that actually ends up reducing oxygen to water, and you generate electricity. So if you have a voltmeter on it, you generate voltage. Okay, so you just made electricity by just
you generate the
electrons.
movement of electrons. Yep.
Right. And now you can also do the same thing. You could use hydrogen as the higher electronegative source, and you can use like a redox coupling. So you could do NAD and NADH and NAD plus, which now we're getting to the physiology part. But if you set those solutions up, you just get a flow of electrons to the hydrogen. So you also then produce energy. And then if you have oxygen on the other side, it would just keep flowing, right? Now we're getting into this idea of, well, how do we actually generate electricity in the muscle? How do we generate energy? And it's essentially that exact same thing. That voltage that's getting generated by these solutions that are passing electrons on, that's what we're doing in the body to generate energy in the form of ATP then. Okay? And this happens, no, it's not electronactivity, but it's kind of the same thing. It's like reduction. Well, I'm hoping to use the proper biochemical terms, but the reduction
potential
capability. There you go, reduction potential. Right? So the reduction potential. It's how much is it going to draw electrons to it. Okay. And so oxygen is, because it's highly electronegative force, it has this high reduction potential. And so what happens is we want to produce energy, and then the first step is that we have like glucose, right? And then we go through glycolysis. What is glycolysis doing? Well, glycolysis, it produces some ATP, but really not very much. You first of all need to input ATP, which means we always need to have ATP around, otherwise you have no glycolysis. You put ATP in the beginning. But the main thing you're getting out of it is are reducing equivalents. Basically, you're getting electrons out of it, okay? So we need to think about what we're trying to do is we're just trying to pull electrons from point A to point B because this is going to produce energy, just like in our solution. So you should want a magnet on one side. You've oxygen, just this electron magnet, it's just going to pull these reducing equivalents through and it's going to make energy. But for that, we need these electrons. We need these reducing equivalents. So that's what glycolysis does. It gives us 2 ATP, is not very much, but it gives us a bunch of reducing equivalents. And it gives us then pyruvate, lactate, which we can talk about after, that can then enter the mitochondria, converts to acetyl coenzyme A, goes into the TCA cycle. And what does the TCA cycle do? Well, it produces some ATP, but not that much, but it produces more reducing equivalents. It just produces more electrons, okay? And these then get spit out and then can be put through the electron transport chain. And what this is basically just a proton pump, okay? So every complex 1, complex 2, and complex 3. Complex 3 is interesting for NIRS because that's where you have cytochrome C, which actually gets detected by NIRS as a detection source, and it's just handing electrons over to complex 4, and it's just you're just basically pumping these electrons through, which is forcing protons, creating a proton gradient, and this is all generating energy. Okay, and this is then generating ATP. So it's really why is oxygen important is because it is in the end just the magnet that's pulling all the electrons through, which is generating electricity, let's say. Okay, so this is why oxygen is important, because of how potent it is to pull electrons. Now, there's a whole bunch of fuzzy business around there. It's more complex than that, obviously, and if we talk about it in more depth, I'm just going to get lost. But this is important for people to know, just like what exactly, it's energy is ATP. Oxygen produces ATP. What does it do? Well, that's what it does. And all this electron is what that ends up producing the most of the ATP, right? So if you just do glycolysis, you get a couple ATPs. If you do the whole process, you're getting 32 ATPs, I believe, 30 plus then the 2, something like that.
Yeah, I think it depends. It depends on how many ATPs come from the reducing equivalents, right?
Yeah, right. And then if you're not doing glucose but you're doing fat, then it depends on the fat source. But with beta oxidation, you end up getting more like 100 ATPs. Okay, so oxygen becomes the super potent magnet to pull electrons through and produce tons of a ton of energy at the end of it. That's why oxygen is important. Okay. Hope that wasn't too crazy, but all that people really need to think of oxygen is as an electron magnet. It's basically generating electricity in that way, and that's how we
Yep.
generate ATP. That's, let's say, the biochemistry of it, rough shot. Okay, why oxygen is important. Now, there's a whole other element to that as well. Okay, oxygen's important. We agree. We need it. This is how we produce energy, and oxygen needs to be around. But then, like, how are we getting the oxygen? Okay, and this is maybe more directly the question you wanted to ask. And this is the oxygen cascade. This is oxygen's everywhere, and we need it, so we inhale it, right? So basically, there's kind of like 4 steps, let's say, that are happening. Okay, 5, but let's go with 4. So ventilation, you're breathing in oxygen, and then there's a diffusion of oxygen at the lungs, so where you're pushing oxygen. So ventilation is like a convective force, right? You're like pulling it in, right? And then you're through a diffusion, you're moving it from the alveoli into the blood. Okay, that's a diffusive force. And then you have another convective force where you're pushing the oxygen because it's now on the red blood cells. You're like pushing it to where it needs to be. Okay, so this is again convective oxygen transport. And then it gets to where it needs to be in the muscle, let's say during exercise. And there again, you have a diffusive oxygen transport where there's a diffusion gradient where the oxygen has to be moved from the blood into the muscle cell. So those would be your 4 steps. It's ventilation, it's a diffusion step, then it's something like a cardiovascular step, right, where you're pushing the oxygen through the blood systems, pushing the oxygen around, and then you have another diffusive step. And then the 5th step, why I said 5th step, is the mitochondrial oxygenation, the mitochondrial function step. It's once you get it in the muscle, it needs to get into the mitochondria where this whole electron magnet thing is going to happen. So it's going to make energy for us.
Yeah, and I should note too that during exercise, your muscle is able to increase the amount of ATP or energy turnover like hundreds of times above resting levels. So when we talk about, getting the oxygen to the correct place, that's really being driven by the muscles and the muscle demand for oxygen. So I just wanted to clear that up for people because that's kind of how your body is deciding, or it's not deciding, right? It's following the oxygen gradient from the highest gradient on the outside in the atmosphere to the lowest gradient, which is actually within your mitochondria, because your mitochondria are using so much oxygen, reducing that oxygen to water. So essentially there's 0 oxygen pressure in your mitochondria. So it's essentially driving that entire pull to just get more oxygen to create the energy needed to exercise.
Yeah, and maybe you said this, but so it's that 100 whatever plus 100 times increase, that's unique to muscle tissue. So muscle tissue is really unique to that. This ability to just like scale up, right? And this need to scale up is what's really interesting about exercise, right? Because when I decide to exercise, this doesn't need like a meditation period of me prepping to exercise. Like I don't have to sit here and be like, oh, I'm going to exercise in 5 minutes, so I better start getting ready to exercise. This can be, I'm getting up and I'm running at top speed. It's just going to be very fast, but it doesn't matter, right? Which means the energy demand at that point in time is peak. I need tons of energy right now, okay? The system's not prepped, essentially not prepped for any of that. And this is where we end up getting these energy systems. And what does that mean? And what does aerobic and anaerobic mean? And a lot of these anaerobic ideas come from, well, if I go from energy demand here to energy demand here, but my, let's say, upregulation of oxygen uptake isn't as instantaneous, then you have like an oxygen deficit. This idea, well, you must be generating energy without that oxygen in place, for example. So it must be something like anaerobic, which is obviously nonsense because there is oxygen around. It's heaps and heaps of studies now that show oxygen is always around. There's always oxygen pressure. Oxygen pressure can't get below a critical value, otherwise you're going to have trouble anyways maintaining cell integrity. And that level is far above mitochondrial functioning levels. So the term anaerobic is probably nonsensical. But to these energy systems that are happening, I do think this is very interesting, because so what does happen is I need energy now, I need energy really fast. So there's like a rate demand of ATP. Okay, and high intensity work has a very high turnover of ATP, right? That's what you need to maintain the work. So I need some kind of systems in place to, first of all, produce ATP very fast, but also produce it very fast, basically instantaneously. And so you have these energy systems, and you have like those sweet like time, duration, and like energy systems, and you get these flowing cascading of events that take place, right? So first note for everyone, that's not like that. They all happen instantaneously at the same time, essentially. For anything sports related, like, I mean, we don't need to say the nuances of biochemistry of what's happening is not relevant in sometimes to applied science, okay? Anytime we start talking about milliseconds, it's like, depending on what you're doing, it can get pretty fuzzy. So, but one of the things is, for all, ATP stores is not an energy system. Okay, so this idea that sometimes you see it on charts, ATP stores an energy system, it's not, because ATP levels don't change. It's not a variable thing. ATP levels stay constant. They're protected. They can't drop otherwise. Basically, fatigue is a mechanism in place to stop you from having too low of ATP levels. It's just like, we're going to make you tired, so you stop doing anything, because the ATP needs to stay like this, otherwise you're going to die. Okay.
Yeah, it would be catastrophic if you ran out of ATP.
It's catastrophic, right? So rigor mortis, welcome. You're not getting, nothing's happening. Actin head, not uncoupling anymore. You're just screwed. So. ATP is not an energy system. It's like a charge that's just constantly in place that you need. So what is the first energy system then? Well, it is probably the phosphagen system, which is this creatine phosphate or phosphocreatine system, which is interesting system because, yes, it's kind of like it's a temporal buffer, right? Because it's basically a reserve of energy that's kind of in place to
it's like a savings account in a bank.
Times. It is, right? So, and that's what people think about of it most of the time, and that's true, right? And this is dynamic. So PCR values change drastically with exercise intensity, but it's also a spatial buffer. So the creatine shuttle, it's basically it helps you transfer ATPs that are getting generated over here in the mitochondria, and the muscles are contracting over here, right? And you need to get ATP to the myosin actin heads. So you can use this creatine shuttle to basically just transfer energy over. So it's not just a temporal buffer; it's also a spatial buffer, let's say, which is an important concept then to kind of remember for later, that how it's important with oxygen. One of the things is then, well, how much time do you have on creatine phosphate? And you get different things, as you'll read like 10 seconds or whatever, right? So not my expertise. You can read about it, but there's some studies. There's an interesting paper by Chung, I think 1998 or so, but they did some above my pay grade PMRS clamp studies, and they were showing that one high intensity contraction lasting 60 milliseconds, you're down 20% PCR. 60 milliseconds. I mean, how many of those? I mean, you're going to be down to 0% creatine phosphate in a second. This doesn't seem to be something that's lasting that long. But what's more interesting is that in between the contractions, you get this big recovery of PCR. So this idea of 10 seconds might just be a lack of resolution into what's actually happening with the use of PCR and the recovery. That's all happening in such a short period of time that for you, it just looks like a slower slope delay, but it's actually like an up and down, right? That's happening.
Yeah.
So, and this, and if you read the Chung paper, they go through, well, okay, that's crazy. There's this super fast recovery that's demanding a lot. So that recovery must be happening from somewhere because it's not happening on its own. So they got to be getting ATP from somewhere. So it's going to be, okay, well, that's got to be the glycolytic system, or it's got to be through oxygen. But if you read some papers by Hathler and stuff, you see that creatine phosphate recovery, which is what we're talking about here from that Chung paper, we're talking about creatine phosphate recovery, is completely linked to oxygen availability. Okay, so if you mix around with oxygen concentration you're breathing, you manipulate creatine phosphate recovery. Okay, so this is this linking of what's happening with your creatine phosphate to what's happening in your mitochondria and oxygen consumption, right? And creatine phosphate acting both the temporal and the spatial buffer between your mitochondria and your muscles. So, which would then, it starts implying, well, this idea of like these cascading energy systems, that you have this phosphocreatine system and then the oxidative mitochondrial respiration system at the end, and in between glycolysis, which we haven't talked about yet, but you have these two like systems and they kind of act in this cascade. That seems to be pretty BS. It's probably just they're both going at the same time, and creatine phosphate's just acting as a buffer for you to get energy from the mitochondria out. Okay. Right. And obviously that flux, that's not fast enough. Like you can't get ATP fast enough. But this is also why max performances don't last very long. Because you can't. You are not going to be able to generate enough ATP at a rate that you need to maintain. That's why every performance like that has like this decline until you find some kind of steady state.
Right.
So and maybe we should talk about the last energy system, the glycolytic system, because it's obviously also important. We talk about
let's talk about the glycolytic system. There's the thing that comes to mind is kind of like the glycogen shunt model, and I don't know if this is like accepted, like very largely, but if you wouldn't mind, just if you could speak to that would be really good, because I think that kind of would lead to a little bit of like the connection, a little bit more of a connection between, like oxphos, glycolysis, and PCR.
Yeah, so that's the Schulman. Oh, what's the other guy's name? Schulman. Oh my God, there's two authors. Anyways, doesn't matter. The glycogen shunt model, go look it up. You'll see the author's names. I apologize. So what's interesting about the glycogen shunt model is it's kind of like the same as Brooks's lactate shuttle. It's very similar. It sets up glycolysis or glycogenolysis and lactate as like a mediator between the phosphagen system and the mitochondrial oxidation system. And Brooke talks about it even more. He then talks about lactate also being the mediator between kind of fat oxidation and glucose or glycogen oxidation. So it just mediates between these energy systems. Okay, and this all kind of makes sense to where lactate is situated. So lactate is generated through glycolysis. This is why we measure it during high intensity. When glycolysis gets activated more and more and more, you generate more and more pyruvate at the end, but probably also just always lactate. Lactate is probably the actual end result of glycolysis, not pyruvate. I know they all show pyruvate, but it's probably lactate. And definitely what happens is if once your mitochondria get overwhelmed, basically you don't have enough mitochondrial capacity, you just start generating lactate because it's got to go somewhere, right? This pyruvate's got to go somewhere.
Right.
So you start generating lactate. And this lactate has a function. And one function is, again, it can go directly into mitochondria and produce more reducing equivalents. It also has a function, actually, that it uptakes protons, it uptakes hydrogens. And this is where Brooks' shunt model comes into play, where this lactate can then be moved around within the cell or between cells. And often then it moves from low oxidative cells, so like white muscle cells, to red muscle cells, which are highly oxidative, okay, with MCT transporters. So they kind of shuttle, as the shuttle model, they shuttle lactate around. And this provides, because lactate then has a function, first of all, to be burned as energy. Like 70% of lactate you produce in exercise just gets burned up as energy again. It's pre-selected ahead of everything. If you have lactate, your blood glucose levels will stay constant. They're not changing. It's just going to draw lactate. Okay. It makes sense. It's kind of like having a piece of wood that you chuck into the fire, but then you realize you chucked way too much wood in the fire, and you're putting the fire out. You just pull a bunch of logs out. What are the logs you're going to chuck back in against one that's burning? It's not like the wet wood outside. You chuck the charcoal wood, just chuck it back in. It's just like further down the process, right? And so definitely losing my train of thought here for a second.
So the importance of
functions,
lactate,
there's a whole bunch of things.
as the kind of
Mediator.
intermediary.
Yeah. Okay, there we go. So yeah, lactate, 70% of lactate is just, but then you get about 25% of lactate is like a glucogenetic precursor. So basically, it's like what is being used to make more glycogen. And this is where the glycogen shunt model comes into play, which is this idea that you're producing this lactate, and you can't do anything with it, so you just shuttle it out. And what does it do? It can then, a bunch of it gets burned up somewhere else for energy, and a bunch of it is just converted back into like glycogen stores. So it's defending your glycogen stores, right? So obviously it's going to keep building down, but it's a way of basically you're being efficient and getting energy back into the system.
Right, and that lactate is being reprocessed into glucose in the liver, and then that can then come back to the muscle and then either be resynthesized as glycogen or used as glucose again to then, ultimately become pyruvate and then lactate and then, so on and so forth.
Yeah, and I think Schulman, if I'm right here, they actually make the argument also that like a lot of glycogen stores are defended through these cycles, right? So if this wasn't happening, your glycogen stores would just deplete way faster. Right? So you need this loop to basically maintain glycogen storage, because otherwise the rate of ATP production through glycolysis and glycogenolysis would be way too high. You just deplete glycogen stores anyways. Okay.
Right. Yeah, this idea that like one energy system gets engaged and then another one gets engaged and then finally, OXPHOS is finally ramped up and gets engaged is is not the right way of thinking about it. I think, these last 10, 15 minutes of this talk, I think what I want to highlight is the fact that all of these energy systems are feeding back on each other in order to maintain ultimately ATP concentrations. So, each one of those systems is important for the other to maintain, whether it's the spatial and temporal buffering from PCR or it's the ATP coming from oxidative phosphorylation that then may be sparing glycogen, or the use of lactate or pyruvate that may be sparing glycogen. All of these systems are in place in order to have redundancies in maintaining ATP stores, because ultimately that's what we're trying to do. Exercise is a hell of a stress, and we need to, like, our body needs to protect those ATP stores as much as possible, because like we said earlier, it would be catastrophic if we were not able to protect that. And, that we're not going to talk about, fatigue necessarily, but we would instantly fatigue if we didn't have one of those systems in place, right? If we didn't have all three of those working in concert.
Yeah, I mean, there's diseases or conditions like that. So McArdle's disease, for example, McArdle's disease, they don't produce lactate. Basically, that whole process of glycolysis doesn't work, right? And they get fatigued super fast, right? Which is counterintuitive to any idea of lactate being limiting to performance. Obviously, you think, wow, they have super performance and produce lactate. No, it's the opposite, because you need the lactate. Lactate is super important for performance. Lactate is basically potentially the mediator also between fat oxidation. So I mean, this is why lactate would be useful for something like zoning for fat max, because increased lactate levels, they affect fatty acid circulation, and they affect beta oxidation levels through HCAR1 and beta ketothiolase, but basically they just downregulate beta oxidation, and they limit free fatty acid circulation. So basically, as you increase glycolysis, you downregulate fat oxidation. Okay.
Right.
So lactate becomes uh, a central player in a lot of these things. The issue with lactate is that it's not always as straightforward when you're measuring it because it's a concentration
Right.
measurement you get. So if you have changes in blood volume, things like that, you affect the concentration. You don't actually know it's directly going in the muscle. You assume it's going up. You assume it's going up in the muscles. Some athletes can't get very high levels, but have huge levels in the muscle. And then you get this idea of lactate tolerance, something to tolerate more lactate, which is all obviously BS. Whereas if you have, highly explosive players, they get huge lactate levels. This probably has lots to do
Mm-hmm.
with mitochondrial function, but also with MCT carriers, like the ability to shuttle lactate around. Endurance athletes are probably really good at that and taking the lactate and recycling it and doing this whole glycogen shunt. Whereas for I'm Canadian, so for a hockey player, it's more important that you shuttle lactate out because it's shuttling protons out. So it's going to stop you from
Mm-hmm.
having an acid situation, not because of lactate. Lactate's helping you, right? So whereas the endurance athlete, it's more about shuttling it back in because you want the energy back. Okay.
Yep.
But this is all not always as straightforward to measure by just taking blood samples.
It's one of those things where it's like theoretically, like lactate makes a lot of sense in terms of tracking it, but then in terms of measurement, it gets really hard and really challenging because when you're measuring lactate in the blood, you're just measuring the balance between the amount of lactate that is being produced and the amount of lactate that is being uptaken. You have no idea what's happening in between. Exactly like what you said. You could have an endurance athlete who's actually making a tremendous amount of lactate, but because their MCT transporters and their mitochondria are so good at oxidizing that lactate, you might see no change in lactate from a blood sample. Whereas, a hockey player may have an incredibly good glycolytic system and a really good ability to ship it out of the cell, but maybe their mitochondrial function is a little bit lower. So then, they would have higher prevalence of lactate within the blood during those high intensity bouts, right?
Yeah, I mean, and it's always like in relation to one another. But kind of even the situation that you say, that's like the best case. That's what we hope for, what it's telling us. Like if we're honest, that is the best what we're hoping for, okay? But it can also be, like I said, if you go to altitude and you get or diuretic situations, you're all of a sudden getting changes that aren't related to more or less. It's just concentration changes. So there's...
Or dehydrated during like heat or something.
Yeah. So there's situations... It's like with everything. This is not, I mean, people be like, well, it's because you're a NIRS guy or something. No, NIRS has its own issues too. I'm just saying all these measurements have issues that we need to be honest about. And one of them for blood sampling is you got a freaking blood sample, which sucks. So, like, that sucks. That's definitely a problem. I mean, lots of people do it. Some people don't do it, but I don't know.
It's just a challenge. It's a challenge of the measurement. Mm-hmm. Yeah, definitely a challenge for the measurement. So now what I want us to do is I want us to make the connection, right? A little bit better of a connection between lactate and then oxygen, and then start to give people an idea of what NIRS is actually doing. Because now we're going to switch from the talk of lactate towards oxygen and then oxygen consumption measured via NIRS.
Mm-hmm. Yeah, so I mean, we can talk a little bit about NIRS, of course. So NIRS is, I don't know, have you talked lots? You must have talked lots about this in your podcast. And I'm just saying things
no, we
haven't said a million times. Really? Okay.
No, not at all. No, this is all really, really good. Okay. I know. We need it. So Roger's the CEO of Moxy Monitor, and we'll get him on to talk technical details about it. Yeah. But we have not really talked too much detail about NIRS and how it works. Okay. So yeah, go into as much detail as you need.
I'll give a brief overview for Roger to then build up on. But
okay.
All right. So NIRS, near infrared spectroscopy, and it's just a happenstance physics that in between 700 and 900 nanometers in the near infrared spectrum, 680 or something like that, that this is an area of light spectrum where you can differentiate between oxy and deoxyhemoglobin. So oxygenated hemoglobin, deoxygenated hemoglobin, they look different on the wavelength. So you can differentiate between the two. How does NIRS work? NIRS works essentially. It uses the Beer-Lambert law. The Beer-Lambert law just says, well, the absorbency of a substance for light is set by like an absorption coefficient, the concentration of the solution, and then like the length of the light that's traveling. That's how you can figure that out, which is why there's a path length problem in general. And so this is what NIRS devices do. They use a modified approach to this, but most of them use this, and including the Moxy. And what you then essentially can do is you can differentiate if you have oxygenated or deoxygenated hemoglobin. On the cytochrome C, that's actually also a molecule that is in that absorbency spectrum, which I mentioned. But it makes up like 5% of the signal, maybe 10. So people are just kind of like, we don't care about it. Okay.
Yeah.
But what is,
so
that it's
I will
just
interject real quick. So I will interject real quick. The way that NIRS works is you shine near infrared light into the muscle, and then from there you can tell based on the amount of wavelength of light that is coming back whether or how much of your blood has oxygen bound to it or does not have oxygen bound to it, because heme molecules are made of iron, and iron binds oxygen. And when those heme molecules are bound to oxygen, they actually change color when they're, compared to when they are not bound to oxygen. So it gives us an idea of just simply shining light in and seeing how much comes back. Okay, well, this amount of hemoglobin has oxygen on it and this amount does not. And that's an extremely simplified version of how NIRS actually works. But I think, without, going into like the Beer-Lambert law and the path length problem and other things like that, I think, that's kind of the concept of what NIRS or near-infrared spectroscopy is trying to do.
Yeah, perfect. Yes. And so for people, there's two nice examples that maybe help people highly exactly. So one is, it from a pulse oximeter, especially with COVID, it's like this little thing in your finger, right? And shines red light through it. Mm-hmm. Okay. And if you hold a flashlight up to your hand, we've all this done as kids, right? What happens to your hand? It like glows red, right? It's because only the red light is that which is still penetrating, right? So that's what you see through it. Okay. And that's why if you put the oximeter in here, the red light penetrates all the way through your finger, and you can have a measurement essentially at the top. Now, the NIRS device that we're using, like you said, you put it on your skin, it sends infrared light in. Most of it scatters wherever, and some of it returns this kind of like banana shape back into the sensor, and that's how we do our measurement, which is what Phil was talking about. And the path length problem is that you don't actually, in order to make the measurement, you need to know what the path length is, but you don't know what the path length is. And so you use something like a differential path length factor, which is you just average everything out. The problem with this is that biological tissue, us, are highly complex, and all these tissues have different properties. Okay, so you don't actually know how the light's traveling through which properties where when these photons return. This is the problem. And there's different ways you try to overcome this problem, right? You time of flight, you try to figure out, well, how long are the photon fling stuff? These are all highly complicated systems. It's interesting, and if you have Roger on, you should talk about that. If you have any nerds on, because I think this is important. Why we think the Moxy works so well is because we think it deals with this problem the absolute best. So now,
better than other continuous wave NIRS devices.
I would say better than time domain and better than, but again, there's people who are going to disagree. But again, but they can talk to. So again, I'm not the expert on that. Roger's the engineer, so we can talk to him about that. But I think it works pretty good, and I've used other devices where I just don't think that when I measure with them, I don't think it makes sense. With the Moxy, when I measure, I just think it makes sense physiologically as to what I'm getting, which is something we'll talk about calibrations and stuff later, if we have time. We're shooting through here.
Yeah, this is going to need to be a 15 episode series all
There
about
you go.
NIRS.
hmm But okay, NIRS is measuring oxygenation. That's the point. We're measuring
Yeah,
oxygenated
yep,
hemoglobin, deoxygenated, and myoglobin. This is what's important, right? It's the transporting
yep.
oxygen and the storing oxygen. This is what we're measuring. Now, we all just learned
Hmm.
oxygen is this super important energy source that we need. We learned how we're getting into the system. So what are we doing with NIRS? Well, we're measuring somewhere in this oxygen cascade is where NIRS is measuring, right? So if we think of a gas exchange system, that's obviously measuring something like at the ventilation part. Okay, and we're making
Hmm.
inferences to the whole system based on input and output at the ventilation. Um, NIRS is actually measuring kind of like at the muscular diffusion side of it. Okay, it's
Hmm.
measuring probably in the capillaries. There's debate about where it's measuring. Probably measuring somewhere like in the capillaries. Um, it's funny, like he's like, you should know that, but like, yeah, well, we don't know that, but that seems to
Hmm.
be where it's measuring. So it's measuring at the point where you're taking oxygen off the blood that you transport it through and you're putting it into the muscles.
Hmm.
So you get this highly dynamic variable that that relates to something like oxygen supply and demand. Now it depends which parameters we're using, but generally I suggest using SMO2, muscle oxygenation or muscle oxygen saturation. And this is the easiest way of understanding this is it's just an oxygen supply and demand metric. It's a relationship between how
Hmm.
much oxygen you're supplying through ventilation and then convective oxygen transport to how much is being demanded through diffusion and then mitochondrial consumption. Um, that's
Hmm.
that's what our NIRS device is doing. Do you want to talk about like
Yeah. So
the different metrics?
yeah, yeah. I think let's just stick with SMO2 today because I
Yeah.
think for those of you who have not heard about NIRS, this is like drinking out of a fire hose, and even people who have heard about NIRS, this is a really good refresher on really what is going on. So what I will add is that we Andrea and I. Full disclosure, both work for Moxy Monitor, which is a company that makes a near infrared spectroscopy device that's available to the public for commercial use, or not commercial use, just any sort of use. And essentially, if you were using a Moxy to measure SMO2, which is skeletal muscle oxygenation, while you exercised, you would just get a number. It would be between 0 and 100%. Say for just the sake of argument, it's at 40%. That number just tells you how much oxygen underneath, or how much of the red blood cells underneath that sensor have oxygen on it. And what Andrew was talking about is actually how that number changes is kind of giving us an idea of the supply and demand between the cardiovascular system and then the muscle uh, demand for oxygen. So if that number, if say we get down to 40 and we hold our power output the same and that number starts to come up, it would be assumed, or we would imply, that the cardiovascular system is delivering more oxygen than our skeletal muscle needs. If that number stayed flat, then we're matching cardiovascular supply with oxygen demand at the muscle. And if that number goes negative, then we're actually outstripping our cardiovascular system's ability to deliver oxygen to the muscle based on how much oxygen is being demanded.
Yeah. So there's always lots of nuance to everything. Essentially, that. So
Right.
the percentage, if we're breaking this real down, SMO2 is the percent. So muscle oxygenation is percent. It's really simple. If you had 10 hemoglobin myoglobins and 5 of them had oxygen, you'd have 50%, 5 of 10. Okay. It doesn't tell you
Right.
anything about how much oxygen. It's a relative value. So you don't know how much that is.
Mm-hmm.
So that's important to know. But we can relate this back to our understanding. Again, lots of people know what an SpO2 meter is. There's a lot of pulse oximeters, right? And if you put that on your finger, you have 100%, okay, or 99.
Mm-hmm.
And this is your arterial. It's the same saturation idea, but it's just the arterial blood. So the blood that just left your heart that's oxygenated, right? That's why this should always be high. If it's low, that's why it was COVID complications, right? It's like you're not loading
Mm-hmm.
oxygen. So that's a problem. Anything below, like once you start going towards 90s, you already have like it's called exercise induced arterial hypoxemia. So you get this big fancy name for it already because it's a problem. And athletes do have this. Some athletes do have this.
Yep.
And that could be something like pulmonary difficulties, right? Because you can't upload oxygen anymore. So it could be a rate problem here. So the idea is that your 100% is coming into your muscles, right? Because you're measuring it here, arterial blood's 100%. So if we have the 40% example that Phil has, that would mean it's something like you're consuming 60% of the oxygen. Now, I don't know how much oxygen it is, but 100% came in, and at least at that muscle point, I measured 40. So it's 60 of that is being consumed. Okay, and that could be a rest value. 40% could be a rest value. That means 60% is being consumed just for the idling of the mitochondria, basically, just to kind of keep the system going. Okay, and then as soon as you start exercising, you can get dynamic changes in this. And usually with the onset of exercise, it almost doesn't matter what you do. So if I had a Moxy on my leg or a NIRS device on my leg, and I stood up and started walking, I would see a dip in muscle oxygenation, okay? And now if I kept walking, what would I see? Well, it would come back up and it would probably even start increasing, okay? Now, if I get up and I start running as fast as I can, I'm going to have the same dip, but it's just going to keep going down and down and down and down, right? And this is where we get to probably the bread and butter of exercise physiology, in my opinion, at least for anything that is somewhat endurance based, which is everything above 200 meters. Everything is endurance, anything. Again, we get to, it's just endurance is your performance curves fall off so friggin' fast that basically everything is endurance. Okay. And so it's about the ability to generate steady state. And this is exactly what I mean in this example. When I get up and I start walking, I get a dip. I have a negative oxygen balance, let's say, because all of a sudden this instantaneous demand for energy, which we said in the energy systems, right? You need to somehow balance that out. And you're going to balance that out by upregulating all these supply systems. So about I need more ATP. So I'm going to upregulate that, right? And if I'm able to, like the walking example, then it's fine. Then I'm just going to walk. I'm going to feel fine. And everything's going to balance itself out again. If the sprinting, if I get up and sprint, I can't balance that out anymore. The body will try, but I can't get it done, right? So I'm not going to find steady state. And so exercise is all about, well, what is the maximal steady state? Because obviously the walking is low. Well, obviously I can go more than that. I could probably get up and jog. But the sprinting is obviously too high. There's got to be something in between. And this maximal exercise steady state is like the gold standard. And this is what make the best endurance athletes are the ones with the highest maximal exercise steady state. It doesn't actually this is also like the idea of VO2 max or VO2 peak are overrated. It doesn't actually matter. Anything endurance based, that doesn't really matter. It's really where can I sustain exercise at the maximal rate for the longest amount of time for my event, which is an important thing. Because your maximal sustainable exercise rate is different for a 2K or 3K or 5K or for marathon, right? So it's important. It's specific to you, and that's where training differences come into play, because you get things like substrate utilization issues or specificity and things like that. But that's the bread and butter right there. And NIRS again does that at this local level. It gives you this local idea of oxygen supply and demand and the steady state component of that.
Right.
Sorry,
yeah, and I will say, I will say that VO2 max is important because it can help to set, a little bit of dictate a little bit of those ceilings of where that metabolic steady state can occur. Because if your VO2 max is too low, then your metabolic steady state may not be able to go higher. So it does play an important role. It's just not when I did my master's degree and we were looking at predictors of performance, VO2 max is not the single best predictor of endurance performance. It's a conglomeration of a bunch of different variables that essentially what you're trying to get at is just exactly like what you said, Andri, is the ability to maintain metabolic steady state for as long as possible, given whatever the event is. So if it's a 30-minute event, that's for 30 minutes. If it's a 3-hour event, that's for 3 hours. And obviously, like you said, psychology and substrate utilization and other things like that start to come into play the longer out you get. But it's all about maintaining metabolic steady state for as long as you possibly can. And Moxy, not Moxy specifically, but NIRS specifically, can give you an indication of are we at some level of metabolic steady state, or have we surpassed that? So So I want to make I want to get your opinion on the connection though between say oxygenation or dynamic oxygenation values and lactate, because I think there's a lot of confusion and a disconnect between, I see people say this all the time. Oh, if we just had continuous lactate meters, we would be able to tell, like exactly when this person was going to fail. And I would argue that NIRS is already essentially telling us that. But I think the gap in knowledge is how does the oxygenation value relate to lactate production? And this is kind of getting into the paper that we did, right?
Yeah, I mean, this gets back a little bit to the physiology, gets back to lactate shuttle, right? So, and like this idea of what's aerobic and what's anaerobic, right? So if you take like glycolysis, like in itself, there's no oxygens involved, so that is in itself something like an anaerobic process. And at the end of that, you can get out lactate. So you're like, wow, this is an anaerobic process. But it's obviously conjoined in this whole system that doesn't function if that oxygen is in place. That's why anaerobic is a nonsensical term in exercise physiology, because if you take the whole, you can't just run glycolysis. That's just not how it works. If the other parts aren't running, it doesn't work. Okay. And so basically, as you go through producing more lactate, you actually then start consuming more oxygen. Okay, those things are related to each other because you need the oxygen's then used again for energy, and you need to use more oxygen for energy. That's why you have this relationship that we see. Okay, because they're related to each other. It's an interesting. so basic. I mean, this is the thing. So when do you consume? When do you have your VO2 peak or your VO2 max? Which we're talking about at the highest intensity. It's also when you have the highest lactate values, where you're the most anaerobic. Those things, none of those things make any sense. Okay, so
if we're thinking about it from the way that we currently think about it, right?
Exactly. I mean, there's no, again, you can split this apart in different ways and make different arguments, but for me, it makes those things all don't make any sense. So in a way, lactate also then helps you drive more oxygen consumption. Okay, because it's a substrate that you're using. And what do you need to use? It's nothing other than the substrate that's helping you create more reducing equivalents for oxygen to pull through to make energy. That's what it is, right? And so the rate at which your oxygen is being consumed is like a meta level, or whatever you call it, lower than lactate. Lactate's at the level of sugar and fat. That's that level. It's a substrate level, right? Whereas oxygen's the level below. It's like where the actual, let's say, energy producing is taking place. Okay, and at let's say the muscular level, as close as you can to get to the muscular level. I mean, this is why there's numerous studies that show this, and I mean, my dad did tons of testing of this, that generally you see a relationship between these oxygen supply dynamics and lactate curves, generally speaking. You will also see relationships, for example, if you deplete glycogen levels, or you change diets around. So, you go low carb diets, you have problems producing lactate, right? No sugar, glycolysis is all down, beta oxidation is all up. So you don't produce any lactate, right? Performance tends to be crappy. Even though you can talk about that. Some people think they have super performance on it, but what also happens is your muscle oxygen levels are generally more elevated and generally have a hard time coming down, because you don't need all that oxygen is not getting burned to try to deal with or try to oxidize lactate, because none of that lactate is coming, and the rate of beta oxidation is generally just slower, right? You don't have that rate turnover is not as high. So I think there's a lot of direct links between muscle oxygenation and lactate, which should be there. And now, so the question is like, well, you're making a good case that lactate seems to be a pretty cool thing to use. And I'm like, yeah, you go ahead and use lactate. But if that can be made in the other direction, at least with NIRS, I don't have to poke anyone and I can get a continuous measurement in a high sampling rate. So they're both usable tools. It just seems to me one is much more useful. There's some nuances there. So I think I think SMO2 is much better. NIRS is much better situated in things like steady state identification. It works better with things like critical power. Whereas I do think that lactate could potentially is better suited for things like actual substrate utilization. Again, because it's at that level. Right? If you
Right.
if you want to hone in something like fat max, you're probably going to be more exact if you take a bunch of lactate measures. But again, you have to take a bunch of blood samples and over again. So
Yeah. And for some people, that's not a big deal, right? Taking a blood sample isn't that big of a deal. And, that's like, okay, like, so use it. But I like that comparison where it's like lactate is essentially at the substrate level. And we can use that to tell us what sort of substrates we are oxidizing. Whereas muscle oxygenation is one step below that and is telling us how is the muscle from a physiological standpoint kind of dealing with the demands of exercise? Are we able to maintain oxygen homeostasis, or is our mitochondria, just kind of using as much oxygen as they possibly can, and our cardiovascular system can't make up for that? And that's what we were looking at during that study that we published, was what is the correlation between the rate of muscle oxygen change at different exercise intensities and the rate of lactate accumulation into the blood. And essentially what we found is that there was a direct mirrored correlation between the two, meaning that if you were using more oxygen and you were more negative in terms of the rate at which oxygen was being used, the more lactate would be excreted into the blood. And that makes sense, right? Because if your mitochondria are limited on how much lactate it can take up and oxidize, that lactate has to go somewhere. And where that lactate is going to go is ultimately into the blood. So you get a disbalance that's starting at the level of the mitochondria in the muscle, and then it's being shown, as increasing concentrations of lactate now within the blood.
yeah, I mean, so lactate accumulation is probably telling us something about like rate of glycolysis, so higher. So like Vela max or something. So like basically the higher the rate of lactate accumulation, the higher glycolysis, right? And so there's this correlation between, the higher the rate of glycolysis, the higher the work rate, the more oxygen that we have to also burn through to try to oxidize lactate, or to try to want to oxidize lactate, because the work rate's really high, right? So we're using this at a very high rate. That's kind of what we see with the slope, right? It's just this higher negative decline. For sure. That's definitely I think it's a really good marker, and it's that steady state marker. So if you have this crazy glycolysis turnover, this negative rate, you're not steady state. If that doesn't get balanced out, you're gonna fatigue, right? And the maximum ability. I mean, and there's papers to this as well. I mean, we didn't do this directly, but there's papers on this. Snyder, I think, did one. That they show that maximal lactate steady state can be identified using NIRS, which again makes sense. Now, all these things are fuzzy because all these thresholds are fuzzy, but
and physiology is fuzzy.
Physiology is funny. Thresholds is funny. The techniques to which how you decide to determine threshold, how you calculate it, protocols use it, it's all fuzzy, but they all kind of something the same. Now, of course, when we're dealing with athletes, you can't be that fuzzy. I mean, if you're 20-watt difference in your threshold identification, but you'll notice it. I mean, it's just like your test will tell you that's like this, and then you'll go ride, and you're like, yeah, that's not critical power because I'm cooked after a minute. So you'll figure it out. And this is also where, again, NIRS is nice because you can just go and ride and see. It doesn't actually matter what the NIRS result was in your test. It can help you do this. You can do a test. You can take a NIRS measure. You can do our 3-minute protocol, you can do a 5-minute protocol, you can do a 10-minute protocol, you can do a ramp test to figure out, what's happening with my oxygen supply and demand. And basically the highest intensity where I can get a zero slope, where I have a plateau, where I have steady state in muscle oxygen, that's going to be critical power. That's going to be critical oxygenation, right? That's just like where I can maintain. and then you go out and ride and you test that, not only by checking what the wattage is and seeing how you feel, but you could throw on a NIRS device and see, well, am I steady state? And am I steady state for the time frame of the test, which was maybe 10 minutes or 20 minutes or 30 minutes? And am I steady state for 3 hours down the road still or not? And with NIRS, that's really easy to do. And with other devices, it's not as easy to do. Hence, that's why I think NIRS is useful. It's not necessarily that it's super better than everything else. It's just like it's easier to use. I can actually apply it to my training, and this is the future. I mean, we had big talk with trainers here and stuff too, because there's a sport institute and it spends a lot of money on complex labs and testing and things like that, which is cool. I mean, I like all that. But there's a lot of talk that the future just isn't in that. The future is in you have the tech on you and you test every day and you collect big data and you do that and not periodic testing. And for that, you need tools that athletes actually want to use on a daily basis. So heart rate's a great tool. Wattage meters are great tools. Blood lactate, less so. Even VO2 masks. I mean, sure, you can say, well, I'll use it once a week, which is already pretty good. But you want to wear a mask in every training? No. So then the question is,
right? Because and then you can't consume.
Is once a week a good enough resolution for you? It might be. It's already way better than doing tests twice a year. Whereas with NIRS, there's no reason why it's not every day, whether it's not in every training resolution.
I like that, and that's how I use my Moxy, my NIRS device. Is I have it on for the warm up, and then I have it on for the beginning portion I just wear it the entire time, and then I'm periodically checking to see, okay, well, based on how I feel, based on how my heart rate is doing, based on my power output, based on my SMO2, am I in a place where, I would expect this to be, say, zone 2? Am I in a place where I would expect this to be, maximal metabolic steady state, or FTP, or, whatever thing you want to call threshold 2 for the day? And I think if we look at like the aggregate literature, this is NIRS really shines at no pun intended at the second threshold portion of things, because it's really the only device out there other than maybe like a VO2 mask that would be able to tell us if we're able in real time to reestablish metabolic steady state. And we have to remember that when you're wearing a NIRS device, it's only looking locally at one muscle. So you might have different things happening at different muscles. So that is one of the limitations that we just have to, talk about and acknowledge. But I do think if you're using one of the muscles that's the prime mover, for whatever it is you're doing, for cycling, vastus lateralis or the rectus femoris, for running, rectus femoris works really good. You get a really good indication of, is this sustainable, or am I already over the edge? And then you can adjust your intensity accordingly.
Yeah. So I agree. So I do think you can use other tools to do it, but again, it's just more tedious. NIRS is just really easy to do that with. It's super easy. It's straightforward. It's one muscle, yes. And we need to acknowledge that and be careful with that. Generally speaking, though, it works pretty well. And there's, there's the Brett Kirby who's on the paper you keep talking about as well. So on a different paper they did forearm measurements with the leg measurements, and they could do the same thing on the forearm.
Right.
So there's some systemic responses that do happen that you can get it. Now, just for like normal users, most people won't have that response in the forearm. At least in my experience, it only happens with elite level athletes. But in elite level athletes or very good athletes, you do kind of get this global response. But there's advantages. So if you have a general rule, right, that yes, it generally works, and then it's like, but it won't always work. There's also advantages to that. So you mentioned, Jem Arnold. Jem Arnold. He's a friend of ours, a great guy. Yep. He knows a lot about these threshold things. So he's an interesting guy to talk to. But his PhD, I believe, if I'm correct, is on iliac artery flow limitations. So basically it's blood flow limitations to unilateral to one leg, and NIRS is pretty well situated to take a look at this because it measures locally. So there's some complications with it, even though the complications generally it's not a problem, but there's also advantages to that, for sure, to take a look at. So I think I look at that as more positive, but maybe just I'm drinking my own Kool-Aid, so I'm just stuck in the spin. This is obviously very possible.
I'm just, try to, I think if you acknowledge, the limitations first and foremost, then people can then make up their own mind. But I do like you taking kind of a different spin on it, right? Because exactly what Jem is doing is he's looking at oxygenation differences between different legs, and one that's affected with iliac artery disease and one that's not. And I'm hoping to get him on the podcast at some point soon. So hopefully him and I can talk about that and dig into that. But yeah, I think every measurement, and I've said this on the podcast numerous times. Every measurement has its limitations and its strengths, and it's just important for us to know and acknowledge all of those. Right? What is it actually measuring? How does that relate to the physiology? And then what can we tell from that physiology? If I was really interested in looking at substrate oxidation, I wouldn't necessarily use a NIRS device. I wouldn't use a NIRS device because I could use lactate, or I could use a gas analyzer to determine substrate oxidation at both the whole body level and then at the blood level as well. So it depends on what you want to use it for as well. And I think there's a place here for all of these. We just have to make sure that we're not overextending, what the potential promise and use is for a certain tool. And we're also just being realistic with what we're actually doing. And I think, you and I have talked numerous times offline about this. It's like, we don't want to overstate, right? What the capabilities of something are. So with the last couple of minutes here, Andri, because I want to be kind of aware of your time, even though I've been taking up quite a bit of it already. What would you say, someone who is looking to start to implement NIRS into, say, their training, what do you think are, the top two benefits and immediate things that they could then do? And I know we've touched on this, but could do to enhance their training or enhance their ability to see changes in their training with NIRS?
Yeah. So, one of them, so I think it can be used for basically, well, as soon as you have a NIRS device, you can do all the classical exercise testing and zoning you can do with a NIRS device. And it's essentially, you can make these things really complicated, but it just think about steady state. Think about going through a profile of exercise intensities from low intensity, high intensity, and figuring out where can I steady state, right? I mean, so you can go through zones. Basically, the steady states you find with the highest oxygenation values will probably be something like zone 2, and the steady states you find with the lowest oxygenation values will probably be something like more like critical power, something like that. It's actually not that hard. People, some people get it right away, and they're like mind blown. They're like, "This is the greatest thing ever," and some people just never really get it. And again, it's hard for me to gauge because I'm in it. Like, I mean, at the beginning of the talk, I started talking about it, and you're like, whoa, and you pulled me back, and you started explaining a bunch of stuff, and I'm like, oh yeah, maybe we should explain that as well, right? You can't see the forest in the tree thing. That happens to me all the time. But so I think that's one. But you're explaining how you use it, okay? And I think I used to wear the Moxy for every training all the time. I used to train a lot more, but and I'd have it on all the time, okay? I don't have it on that much anymore. This has nothing to do with, I think it's a great tool. This has to do with a lot of my training is meditative. I just I don't want to do anything. My head's just like, I'm here to just breathe and hurt myself. Like, it's just like, I don't have that much time. Okay. Especially, and I do lots of rock climbing and outdoor sports, or like in the gym and like strength stuff, nothing in years. But where I do use it, because I think it's super useful, and it's an easy way. And it goes to this strength. It's the strength of identifying something like critical power. It's this threshold 2. I use it. I do like 4x4s, right? So I do 4 minutes, high intensity, and then 4-minute breaks. So these Norwegian methods, some people call it whatever, like these VO2 max intervals. And that I think is one of the best things and easiest things to use it. So either you can go ahead and do a VO2 max test and find out what your NIRS value is at VO2, and then usually you up it a couple percents up, and then you're like, this is what that's the number I'm pointing at. So I want, if that's 20%, then I want to go to 20% and hold 20% for 4 minutes. And then I'll take my break and I'm going to repeat. You can also kind of just do like a minute or two pretty close to all out and find out with loss of performance where it stabilizes at, kind of like a 3-minute all out test. That also works. You find critical oxygenation like that. It's just basically like the lowest SM2 value you can, where you can kind of stabilize it out, tick it up a couple percent, and then you're good to go. So for me, that's like about 23%. And it's pretty stable at that. So I just like my intervals, like I go 4 minutes at 23%, go. And it's super motivating. That's why I love it. I just like, it's 20%. And if it starts going up, then I'm like, either I can't, I'm just done. Like I'm actually contraction failure, and then, okay, screwed, or pussy, just keep going. And then I push a little harder, and then I can maintain, right? So, I mean, it's beautiful, and it really gets me to go hard on those VO2 max intervals. And it also makes, I don't do by power. So sometimes, the power will be 20, 30 watts higher or higher because I'm like, I'm feeling great. And then I'm not pushing whatever it is, like 250 watts or something. I'll be like, I'm doing 270 or whatever. And so outing my crappy wattage shit might that doesn't matter. So then I'm pushing that. But the same goes if I'm like I'm like, oh man, I feel terrible, I can't get it down, or I feel terrible, I'm at 23 and I got like way less wattage because otherwise it's going to keep going down, or I can't get to go down. Then it's also like, well, today probably not worth it to do these. I'm just not going to get the stimulus I want. I'm over fatigued. Let's just take a break. Let's try again tomorrow or try again next week, depending on the time I have. And I think that's a really easy way to use it. It's a super effective way. It really hits the strength of it. It's a motivating tool. It's a monitoring tool. And you can really then track performance increases, right? And what will happen is for people, less fit people, it'll be like 40%, let's say, or 30%, and you'll find it'll go down, and it'll actually track with increases in VO2, VO2 max. So, it's very.
And you'll be able to see too, say for example, if you hit, like, you could also get it to a super low point, right? Maybe like 15% for your VO2 max workouts or something like that. But as you get fitter, that 15% is going to come at 300 watts, 320 watts, 330 watts. The wattage that you're hitting, that 15% is also going to come up. No, I really like that, because that actually allows people to get away from wattage in a sense. And I think a lot of the times, like I run into this issue, is that when I prescribe myself wattage goals, say, okay, I got to hit 400 for 30 seconds, or like a minute or whatever it is, and I haven't done that in forever. I'm artificially inflating my wattage numbers now, but
man, I believe you.
Yeah. As opposed to doing that, if you all you have to do is just say, ride on your bike, and then every minute increase the power output, 20 to 30 watts, and then just go until you reach failure. That's essentially what a VO2 max test is. If you have a Moxy on, you'll see where that low SMO2 is. That's where you're going to ride your VO2 max workouts at, is that percentage. And then, like Andri, like you said, some days you can't even get that, get to that, say 23%. That's an indication that you're still fatigued. Something is happening where you're not able to actually pull as much oxygen out as you once were able to. So you gotta back off that day. So it's also then a recovery tool, and then it's a motivation tool, because now you're like, okay, as opposed to being like, I'm going to hit 400 watts, but I feel like shit today, or I feel really good and I'm still only going to hit 400 watts, you're going to hit 23%, and then you're going to be able to hit whatever it is, your body is able to do at that 23% for that day. So it's a self-modulating tool that's actually responding to your physiology, not the mechanical output that you're actually giving on that day. So, for those of you who might need a little bit of a break from power, I think like a NIRS device would be extremely beneficial. It certainly has helped for me. And then, the break points, right? Everyone, like if you're listening to Peter Attia, or if you're, talking about polarized training, and we're not going to go into all of that sort of stuff, but finding where your zone 2 is, and then finding where your second threshold and your VO2 max is super important. But a lot of us don't have access to, say, a lab. So you can do the same sort of test you would do in a lab, where you do 3 minutes, or 1 to 3 minutes at a certain, I would say this is what you'd have to do. You'd have to do 3 minutes at a certain wattage, and then bump up probably 30 watts, do 3 minutes, bump up 30 watts, do 3 minutes, and keep doing that until failure. And then you're going to look for, exactly like what you were saying, those changes in steady state, from maximal oxygen levels to then it's going to come down, and then it's going to potentially reach like lower oxygen levels, where you can actually reach a plateau in a steady state, and then it's going to hit that tipping point. And now you have your zone 2 training. So, like the power or the percentage that you're going to work at for your zone 2, you have your, an idea of where your threshold is, and then you also have the VO2 max, SMO2, so now you can hit all 3 of those types of workouts. And all you need is just a little NIRS device on your leg.
Man, we forgot to talk about all the mitochondrial function testing, and like the creatine phosphate and those relationships, and my whole energy systems talk. I completely blanked on all that. So happens when you don't have a structured layout, and I'm just spitballing off the top of my head. I leave out tons of really important details. But on your point, man, we're gonna, like, athlete readiness is just like a huge thing that you just brought up that we use a lot. Like, we know what your NIRS response is, what your NIRS numbers are for a given wattage, for a given output. If it's running, whatever, is it the same as what I would expect? And so if it's, it can be positive. You're like, oh man, again, like I said, I'm like, all of a sudden I'm upping 20 watts. I'm feeling great. I can maintain things. It's like I'm optimizing my training, right? I'm really not sticking to 250 or whatever I said, and then going to 2. So I can really use like a good training day to really kind of push stimulus. But it also just like, then, no, you're not ready to train today. And there's papers on this. I did a paper with climbers on that kind of reflects this. There's a bunch of Ahmadi papers on this, that basically, your NIRS signal will respond to something like readiness, to basically muscle fatigue. Right. So there's a paper on trail running. Post trail running, you just get an inability to desaturate. Right, like eccentric workload, muscles get toasted. No contraction, no muscle, no oxygen consumption. VO2 is also way down. So it becomes it's an interesting aspect to consider, that in real world settings, I've used quite a bit in decision making. There's research around to support it, but there's also obviously always open questions. But yeah, I think that's definitely a valid way of using it. I mean, you triangulate everything. I mean, you kind of said this. You never make decisions based on one data source. And NIRS is just an easy data source that gives you something else to triangulate onto decision making. I mean, any good coach knows decisions are generally this or this. Okay, probably more this. So let's do this, right? And you try to hopefully have some information to help you kind of push it in one direction. And just don't tell the athlete that you don't know what you're doing. I actually don't agree. You should always tell the athlete what you're doing, but some athletes don't take it that well. If you're honest, I tend to be really transparent, and some athletes deal with it well, and some athletes are like, I need a new coach. You don't know what you're doing.
Yeah, no, I know. I know it's really interesting, right? But that digression aside, there's so many things that I think, there's potential for NIRS to actually, like have the capabilities of, and we'll have to jump on another call at some point and maybe have a little bit more structure of what are the other applications of NIRS. But I think this was a really good overview of, like not only like the oxygen cascade and the tying in of all of like the bioenergetic systems, how lactate is related to oxygenation values, and then how NIRS can actually start to track and monitor that. If you guys have any questions, you can reach out to me, as always, on Instagram at Critical02. Andri, what social media can people find you at?
If any. On social media.
Okay, well, if you have any questions...
but I don't have time for it anymore. But if people want to ask me something, they contact you, and you can give them my email address.
Yeah.
So people email me all the time. That's the best way.
Okay. Yeah, I'll do that. If you have any questions for Andri, you can also like find most of his papers are probably open source or probably readily available through ResearchGate and stuff like that. So, search Andri Feldman. His name will be in the description
I'm on
below.
ResearchGate. There you go. That's what I'm on. I'm on
Yeah,
ResearchGate. That's my
there we
social
go.
media platform. I'm on ResearchGate. Go check. That's
Yeah.
actually up to date too. That's the only thing that I somewhat keep up to date with because I actually communicate with
Perfect.
people on ResearchGate. So that's the one. I'm a nerd there.
Perfect.
ResearchGate.
Yeah, no, that's perfect. So if you want to read any of his research articles or read the research article that him and I did together with Brett Kirby, who is the physiology director of the Nike Breaking 2 project, not to flex on that too much, reach out to me and I'll send you the paper. Yeah.
Brett's great, man. You should have him on. If he comes on.
If I ever get enough time with him, I will for sure get him on because he's amazing. Maybe for future episodes. But if you guys are on Spotify, you can go ahead and you can leave a comment, leave a 5-star review if you've made it to an hour and 20 some minutes into this episode because I know you like it. If you guys are on YouTube, you can comment down below any questions you have about NIRS, use of NIRS for training or anything like that, and I'll get back to you. We really hope you guys enjoyed this conversation. I sure did. It got into the nitty gritty and the physiology, which I always love to dig into. So I hope you guys enjoyed it, and we'll catch you in the next one.